Alright, here we go. Chapter 10 review thing from the book. Right. It says you need a calculator and a standard normal distribution table. Well, you could use a standard normal distribution table, or you could use your TI 81 or 84. Gosh, 81. Where'd that come from? Somebody said they wanted to use the tables. That's fine. I'll show you everything here though using the calculator. All right. Basketball player has a free throw percentage of 82%. Draw a histogram of the binomial. Okay. So one of the things in this test I'm worried about for you is the difference between when you're supposed to use binomial and when you're supposed to use normal. Okay, so this one they tell you. Remember binomial, well, I'll get into it as we go. Probability distribution for the number of free throws a basketball player in 6 attempts. This is like the multiple choice kind of thing. We're going to have a histogram showing what if he makes 0, what if he makes 1, 2, 3, 4, 5, or 6. I don't really know if I want to go over this space or this bar or whatever I want to do. Anyway, I want all these different heights. So we actually need to know what's the probability of 0, what's the probability of 1, what's the probability of 2. You could just actually make a histogram on the calculator. You could make the scatter plot of the 6 different heights, like kind of like that. You could get the list and just plot the heights here. Let's just produce the list first so you know what that's like. Alright, so I want all the separate probabilities of 0 through 6 successes if the probability of success is 82%. So that is a binomial distribution, also because they told me that. That's a binom PDF. Number of trials is 6. Probability of success is 82%. And I'm going to go ahead and store that in my favorite place, L2. Now, if I want to actually see that list, the best way I could scroll through this list, or I could actually just, since I saved it as L2, I could go look at it here. Oh, here it is. You can see it there. And here's my list. And I could copy these heights down as the height of my list. Fine. Or I could label this 0. This is the whole reason why we kept L1 open the whole time, is just for this reason. I could actually label my, this is my X column. And that should be the end of the list, right? Nothing below that. Good. So 6 successes is about 30%. So the highest thing in here is 40%. I could actually just graph this as my X and Y points and use those as my height here. I know the highest one has to be about 40%, which is good when you're making a graph. Actually, I'll do that now. So if this is supposed to be 40% is my max. I'm going to go here for 2, 4, 6, 8, 10, 12, 14. I don't know, 15, 40%, 14 little spots. I guess I could go by like 10, 20, 30, 40. That's kind of low, though, I guess. I could go 1, 2, 3, 4, 5, 6. These could all be like 7%. Like I call that 0.07. Oh, that'd be funky. 0.07, 0.14. Look how this is going to work out. This is cool. 0.21, 0.28, 2 more tick marks, 0.35. 2 more tick marks. Wow, that's non-standard, but it's going to fill up the graph better. Now, you could do this however you want. I'm just going to use those as mine. Because I know the tallest one's supposed to be about 40%. If I did it by 10s, it'd be like way down here somewhere. I just wanted to fill that up. Okay, yeah, I could just go plot these. You could make the graphs paper sort of plot these too. If I went to my stat plot and plotted this as a... I'll just do it as a scatter plot. That you can do histogram, but it's really hard to make it do what you want to do. And L1, L2 is all I want. Zoom stat, and it should give me a nice little, yep, there it is. So that's what the heights of the bars look like. It's really swoopy like this. Yeah, and you have to plug those in anyway. So this kind of helps. At 0, it's really close to 0. At 1, it's really close to 0. At 2, of course, this is from the chart. At 2, we finally get to like 1%. So this was 7 here. So 2, we finally, this is 3.5. So at 2, it's like, right there. This is like almost too small to care, almost too small to care. At 3, we get up to 6, almost 7%. So that's like here. Oh, it's supposed to be a histogram. I guess I could widen my bars a bit. Bar graph is fine if it says histogram. 4 is 21, almost 22%, which is like there. 5 is... This is really exciting to watch, I'm sure. 5 is right at 40, which is why I made this graph so tall, which is like, I don't know, 35, 42. It's probably like, well, that'd be 38.5, so it's like there. And 6 comes down a bit, I think, right? Yeah, 6 is at 30, which is kind of in here somewhere. Okay, so that's what your bars look like. And actually, for histogram, I should shove these together. But anyway, that's the kind of swoop we're supposed to get. Describe how the domain, range, and shape of the binomial distribution here would change if the basketball player's free throw percentage were 0.5. Well, you could just go back and redo this and go, okay, it's still going to give me this. This graph is sort of dynamic now. If I restore this, I mean, you're supposed to be able to predict this, but if you can't, you're supposed to predict that half would make it really symmetrical. But let's say you can't predict that. Let's say the percentage is 0.5, and let's just restore that as L2. That'll automatically change the graph because the graph is operating on L2. So boom, watch that. Ooh, look at that. Ding dong, it's a bell. So, how the domain, range, and shape of the binomial distribution question 1 will change as basketball. Okay, so I'll say wave, crest, moves left. You could say graph is symmetrical. That's nice too. At 50% pass-fail rate, you're going to get symmetry. At the line of symmetry, there was a quiz question about line of symmetry. X equals 3 is the peak of that, which is the expected value now. Expected value is NP, and NP is now 3, and that's going to be the mean. And it's starting to look, that's when we start to look like a normal distribution. Now, I think the population here, the number of trials here is too small for it to be a normal distribution, but it's starting to take on that shape. Okay, great. Number 3. An experiment is conducted in which a fair 6-sided die is tossed 60 times and a number of times a 5 appears is counted. What's the expected mean and variance for this experiment? Okay. N here is 60. We're headed for, now here's the thing, the plan on this thing. Are we talking about not normal PDF or normal distribution? Are we talking about a binomial distribution? Are we talking about neither? This one, it's really just asking about mean and variance. You know what? I wouldn't ask you variance. I'll tell you right now. I'm not going to ask you variance. Well, let me answer this stupid question. I'll tell you what I would ask. Variance, remember, variance is actually standard deviation squared. I would probably ask you instead, substitute in here, I would ask you for standard deviation. I'll just tell you that right now. I'm the one who makes the test. I have inside information. That's actually going to be standard deviation. This is a fine question, but I wouldn't ask variance. I'd ask standard deviation. So I'll do both these things. You have to find this before you find that anyway, so it's not totally weird. Anyway, this is not asking about a distribution. This is not asking about a probability. This is not asking about, significance levels or how weird is it that something happened. Is somebody lying? Is somebody unfair? It's just simply asking what's the mean, what's the variance. So I need to know mean, and I need to know standard deviation so I can find variance. Mean is good old n times p, and standard deviation is good old square root of npq. So guess what? npq is variance, if you really wanted to know. That's not very good looking. Sigma squared would just be npq. So, I mean, we're going to find it in the process anyway. And here we just found out n is 60. What's p? Probability of rolling a 5. Success there. Probability of rolling a 5 is 1 out of 6. Now, the calculator, of course, doesn't like that. Oh, no, we're not doing distributions. We can just leave that as 1/6. Probability of failure, because we're going to need that, is then 5/6. And these are the things we need. N times p, then, is 60 times 1/6, which is something I can do in my head. That's 10. And which makes sense, right? I mean, if you're rolling a die 60 times, how many 5s would you expect to get? Well, 10. I mean, you expect 1/6 of those to be 5s, and 1/6 of them to be 1s, and 1/6 of them to be 2s. So that makes sense. This is the one that's really not predictable. This is going to be the square root of n times p, which I already know is 10, times q, which is 5/6. So this is the square root of 56. So guess what? Variance is 56. Oh, I can reduce that. That's 25/3. Oh, and I can do that sort of in my head. That's the square root of 25/3 is 5 over the square root of 3, which is really not spelled correctly. I should call that 5 square root 3 over 3, which has probably got a decimal equivalent somewhere, but you know what? I kind of like that. Yeah, 5 square root 3 over 3. 5 square root 3 over 3, I could decimalize, but, why be so uncouth? All right, number 4, which of the following is not true of this? Now, this is the parent function. That's what we call this. This is the parent function of the normal curve. That's the weird one. This is the one that does not yet behave like a probability distribution. This is the one where the area is too big and the height is too high and the inflection points are in weird places. So what's not true of it? Well, let's draw it and talk about it. It is centered at 0. Gosh, that's a really bad drawing. The peak here, though, is 1. The inflection points are weird. They're not 1 and -1. They're like, you know, this. Are you supposed to memorize all this? No. You're just supposed to be able to answer this question. I'm maybe going overboard here. The area is not 1. That's really the thing to memorize here, is that the area is not nice. The fact that it's actually this is just sort of a cool bonus idea. The fact that this is actually square root 2/2, not a big deal. But the fact that it's not 1 is the big deal. Oh, yeah, that's negative. Yeah, and everything else is sort of like the standard normal curve. All right, and the fact that this one is not the equation of the standard normal curve. The standard normal curve is the one that's got the 1 over square root of 2 pi in it, and the exponents divided by something, or divided by 2, and all that stuff. All right, function at 0 is 1. Yes, that's true. That's one of the things you should know. The function equals the negative value. The function at x, like over here, equals the same y value as the negative version of that x. Yes, in other words, it's even. That's like saying it's an even function. That's true, so it's not b. The function is always decreasing. Well, over here it's increasing. That means as we move left to right. That's what they mean by always decreasing. It means as you move left to right, the value of y is always going down. Well, it is from here on. But back here, this range here in this zone, as x goes up, y goes up. So this is not true. We're looking for stuff that's not true. Function has no minimum. That's true, because it has an asymptote at 0, of course. So it never quite gets down there. What's the minimum value it ever takes on? I don't know. Give me a positive number, I'll find you a value of y farther down that it eventually gets to that's below your value of y. So it has a limit at 0, but it never actually has a minimum. The minimum is above 0, but we don't know what it is. It's infinitely small. I love those kind of arguments. That's a weird question, though. That part D. Part C is obviously the false part, though, on that one. All right, in 5 and 6, z is a continuous random variable with a standard normal distribution. Great. Find the probabilities. All right, so we're talking now normal standard distribution. This is where you would use normal CDF on your calculator. Again, they told you that, not binomial. You'd use normal CDF. But here we're just, since it's standard, you only need upper and lower. You don't need to worry about mu or sigma here, because they're going to be the default values of 0 and 1, so we don't have to worry about that. All we just have to put is upper and lower. So if here it's supposed to be between, remember the inflection points are at 1 and -1, so it kind of looks like this. We're supposed to find the probability from 0 to 0.69, that's right around here. We're supposed to find kind of this zone of probability for number 5. We just have to go there, go normal CDF, and we're just going from 0 to what they gave us as an upper limit, and I don't have to put anything else in. That's it, and it's about 25.5%. That they want as a percent. Probability, and you could put this as a percent, or you could just put it as a decimal. I don't really care. So that's that one. So I've done that one there. Oh, really? I can't just erase part of that, or just take part of that out? Okay, so that was part number 5. Number 6 is that the absolute value has to be less than 1.2. So here's 1.2. If the absolute value is less than 1.2, okay, so it could be in this area. These have absolute value of less than 1.2, of course, because they're positive numbers between 0 and 1.2. But also there's some numbers over here that have an absolute value of less than 1.2. That would be everything down to -1.2. So really what we're talking about is all the stuff down to here. From -1.2 to +1.2 will be in this zone. So my lower limit, same thing, but my lower limit is, I'm about to run out of time. Lower limit is -1.2, top limit is +1. So I put that in, trying to save time here, last few seconds. It's about 77%. There you go, and that will be the end of part 1 here at number 6.